Hey everyone, and welcome to this explainer. As your resident engineering professor, I am absolutely thrilled to take you on a journey today, where we're going to take the complex, sometimes intimidating mathematics of fluid dynamics and anchor them firmly in real-world physics. Today, we are unlocking the secrets of turbine power. We're going to take those dense textbook equations and translate them into the physical forces that literally light up our cities. Okay, here's our game plan for today. We'll start with the macro anatomy of a turbine, unpack the velocity triangle, look at the physics of fluid impact, calculate the jet force, optimize our blade curvature, and finally, bring it all together to maximize hydraulic efficiency. Let's dive in.
Starting off with Section 1, Anatomy of a Turbine, the macro view. Now, before we even touch a single equation, we've got to ground our understanding in the actual physical machinery we're trying to optimize, right? Because engineering isn't just math in a vacuum, it's math applied to metal. Just take a look at this gorgeous cross-section of a Francis turbine. The massive challenge here is capturing energy from water as it enters that outer spiral case, gets directed by the guide vanes, and then violently impacts those spinning runner blades in the center before dropping down through the draft tube. Every single drop of water transfers a tiny bit of momentum to that runner, which spins the main shaft.
To really understand the math behind that violent impact, we have to wrap our heads around a fundamental concept: relative velocity versus flow velocity. Think about one of those moving walkways at the airport. If you're walking on the normal floor, your actual speed is like flow velocity. But if you step onto the moving walkway, your speed relative to someone standing still right next to you on that same walkway, that is your relative velocity. In our turbine, the water is moving, sure, but the blade is also running away from it. The relative velocity is the speed at which the water actually catches up to and strikes the moving metal.
All right, Section 2, Unpacking the Velocity Triangle, the micro view. With that physical reality in mind, we can start translating the water's motion into geometry. Let's visualize that exact fluid impact on an unsymmetrical, moving curved plate. Notice how we clearly contrast the inlet velocity vectors on the left side of the blade, where the jet strikes tangentially to the curve, against the outlet velocity vectors on the right side, where the water finally leaves. At the inlet tip, bounded by points A, B, and C, the absolute velocity of the jet is broken down into components. The water strikes, follows the curve of the blade, and exits at the outlet tip, forming a completely different geometric triangle on the right. So what's the secret sauce here? It's all about comparing two specific horizontal vectors, the whirl velocities. On the inlet side, the inlet whirl velocity represents the component of the water's speed that is actually driving the blade forward, in the direction of motion. On the outlet side, the outlet whirl velocity represents the residual swirling energy that's just leaving the system. The relationship between that initial inlet push and the final outlet release completely dictates our energy transfer.
Moving on to Section 3, the physics of fluid impact.
To accurately calculate that energy transfer, we need to set up a few foundational physical assumptions to make the math manageable. First, if we assume the metal vane is perfectly smooth, meaning no friction is slowing the water down as it slides across the curved plate, then the relative velocity at the inlet exactly equals the relative velocity at the outlet. Furthermore, because the entire runner is spinning as one solid piece, the physical tangential speed of the vane itself remains constant, so the inlet and outlet blade speeds are equal, which we'll just call U.
Building on that, we need to look at mass flow. Basically, how much water is actually doing the hitting. It's simply the density of the water times the cross-sectional area of the jet multiplied by that relative velocity we just talked about. Remember our airport walkway analogy? We don't use the absolute speed of the water, we absolutely must use the relative velocity because that is the actual rate the water is colliding with the receding blade. Okay, Section 4, Calculating the jet force, step by step. Let's see how this all builds into the mathematical derivation of the physical push against the metal blade. We're just applying Newton's second law of motion to our fluid. To cut through the dense math, we're going to follow 3 straightforward steps. First, we determine the mass of the striking water per second, which we literally just did. Second, we calculate the initial versus final relative velocity components strictly in the direction the blade is moving. And third, we multiply those together to compute the total force exerted by the jet. Step 2 is pretty visually striking. By contrasting the inlet velocity component with the outlet relative velocity component, we see a totally crucial difference. The outlet component is negative. Why? Because the water is now being directed backward, in the exact opposite direction of the blade's travel.
This dramatic change in the water's direction is precisely what applies physical force to our runner.
So, executing step 3, we combine our mass flow and our velocity changes, and it yields this beautifully elegant equation. The force in the direction of motion equals the mass flow rate multiplied by the sum of our whirl velocities. And notice how those blade speeds, the U terms, they completely cancel each other out. This single equation perfectly represents the total physical force the water exerts on our turbine blade.
Which brings us to section 5, optimizing blade curvature and the all-important beta angle. Now, you might be wondering, what happens if the turbine manufacturer messes up? What if they design the physical curvature of the blade incorrectly? Well, our entire force equation hinges on the angles of that velocity triangle, specifically the outlet angle known as beta. Look at how sensitive the math is here. If the outlet angle beta is exactly 90 degrees, the water leaves completely perpendicular to the motion. Mathematically, the outlet whirl velocity drops to 0. Our force equation shrinks, and we lose that added boost. We're just not fully capitalizing on the fluid's energy.
But wait, it gets worse. If beta is manufactured as an obtuse angle, meaning greater than 90 degrees, we have a massive, unfortunately common design failure. In this scenario, the math literally subtracts the outlet whirl velocity from the inlet. The water is effectively fighting against the forward motion of the blade. You end up with a poorly optimized, severely underperforming turbine.
So optimizing blade curvature is mathematically absolutely critical. This general force formula tells the whole story. A smart, acute beta angle adds to your force, maximizing your output. A poor, obtuse angle subtracts from your force, ruining your energy transfer. The geometry directly dictates the power. It's as simple as that.
Finally, let's wrap up with section 6, maximizing hydraulic efficiency. Let's zoom back out to the macro level, because force is great, but what we really want is work, right? Work done per second is simply our physical force multiplied by the distance the blade travels per second, which is its velocity, u. By multiplying our force equation by u, we successfully translate the water's impact force directly into mechanical shaft power. This is the actual energy available to spin the generator. But how good is our turbine at actually doing this? To find our hydraulic efficiency, we just divide that mechanical work output by the initial kinetic energy of the incoming water jet. It's the classic engineering question. What are we getting out versus what did we put in? The input is simply the raw kinetic energy of the water.
When we plug all our terms in, we arrive at this final, brilliant equation. This proves once and for all that maximizing energy transfer relies entirely on how well we balance those inlet and outlet velocity triangles through careful blade optimization. You want the highest possible work output on the top of that fraction, which, as we now know, requires an acute blade angle to ensure we're adding, not subtracting, our whirl velocities. As we wrap up this explainer, I want to leave you with a thought to ponder. If we can squeeze this much efficiency out of basic trigonometric velocity triangles today, what kind of futuristic, organically curved shapes will power the massive hydroelectric dams of tomorrow? With modern computational fluid dynamics letting us simulate millions of variations, the perfect velocity triangle of the future might just be a shape we haven't even imagined yet. Thanks so much for joining me today. Keep questioning the physics around you, and I'll see you in the next one.